Okay, hello everyone. Another Advent of Code video, and today we get some rest. Actually, some very let's say trivial puzzle. So what do we get? We have some coordinates here, which are basically some voxels, so some cubes in space. One by one cubes with those coordinates. Simple enough. And there's the question: how many sides of those cubes are not touching another side of another cube, right? This is the part one question. And I mean, how to approach this kind of question? So let me draw it quickly, or maybe not. Oh, another screen again. Okay. So there's the idea that let's think about it in 2D, which would be way easier to present. We have some squares, which are 2D cubes on the surface, right? Like this, on some positions. But for example, here I would have this kind of two squares and so on. So how many squares sides are on the outside? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 8, 9, 11, 12, 13, 14, 15, 16. And basically the formula for this is how many sides are there in total. So this is like 4 times n, where n is number of those guys. So 1, 2, 3, 4, 5, which is 5, right? Minus, I need to subtract faces which are common. But I need to do it twice. So 1 time for each square. So it's 2 times 2, right? Let's call it 2 times c, which is commons, right? So this is how we can approach this. And in this case, it is 20 minus 4, which gives us 16. In 3D, this is exactly the same thing, except every cube has 8 faces. 6 faces instead of 2 faces, so the formula becomes like 6 times n minus 2 times commons. And the only thing here is to find commons. How do we do that? Very easily. There are a couple approaches to that. So what I did myself was I checked my input. Let me give me my input. I checked my input and I said, okay, that I don't want to go through all those things, and I don't want to figure out how big is my area I need to scan. But I see that there are not so many points, and in my head there was already solution which was basically linear in terms of number of points. So I decided I don't care about allocating like space as a cube or something like this. I don't try to optimize it. I keep my points in hash set. So I just keep coordinates of points which are existing on my area, not a surface, right? Not even area, on my volume or something. Anyway, on my space, space is the proper one. What do? I have only one main function. I don't split it. It's too silly of a task. I read my lines. I split my lines into the vector. It's mine. I don't care about efficiency at all. I just want a quick solution. And yeah, I extract them to tuple so I can easier work with them. Then what I want to know is that's hidden. I need to figure out how many hidden faces are there. So if I have them in my hash set, that would be exactly the same easy if I would have them in some space like 3 by 3 by 3 space, or like 100 by 100 by 100 space. I would need to figure out how big is the potential space, right? That's the only problem. So because I have like the only thing I need is very quick check if there is another if there is particular voxel there, right? If I would collect them in vector, then I would need to just scan the vector. Now I don't need to do that. I just can ask hashset, is there such a point, right? So what I do for every cube I have, I am looking to for another cubes on like with one coordinate changed, because those are coordinates like touching my face, hitting my face. So I just created this array, I iterate over it, and I filter those arrays which contains which are in my dataset. My dataset are my points. If a neighbor, this is neighbor stable. If my neighbor is in this dataset, that means that we share the face, and I just added my result. Then I I actually just count how many neighbors I have. So for every cube, I map them to how many neighbors it has, and then I just sum it, and then I calculate my data length times 6. So total faces minus hidden, not twice 2, because I mean every face would be detected for both neighbors, so it's already times 2 here. So I just subtract hidden, and this is the whole solution for part 1. And part 2 is a bit more complicated. That requires something. So let's go back to our drawing quickly. So there's a thing that it may be a case we have something like this. For example, we have square here, here, and here. Let me shade squares, because this central one is not a square, but I want to only detect such squares here or cubes in my solution that are that I can basically write directly, so I can reach them directly from outside. So I will not count those guys because I cannot reach them anyhow. And this is not like this trivial, but it's still very, very simple. So how we can approach that? We can just implement fluid field. How does it work? So let's just draw quickly a surface like this with some pixels. Like do it real quick, like something like that. And how fluid it was, but maybe shade some cells here. Shade this and this and some stuff. So those are shaded. Maybe another shape here. And something like here, which is not enclosing anything, and maybe the last one here. So this is my surface, right? And those are my cubes, which are 2D, so they are called squares, or however you want to call it. And how fluid field work? I need to pick a single point on my grid, which I know is interesting for me, so I can reach it. So I choose this square for my starting point. For now, I don't yet know how to figure it out. So I pick this. I have this, and what do? I just need to visit my siblings. So I go here and here and here now, and then I go here and here, from this and from this, here and here, and from this here and here. There's a problem that, I mean, very like natural way to do it is to do it recursively. So I go here, and then I call my fluid field recursively for this, and then from this for this, and so on. So this is a problem, because this way we would have very deep recursion. For this very task, it would be over 5,000, I think, or almost 5,000 1000 for my input. I just checked it from curiosity. So this recursion is not the best in this case. In previously when I was talking about recursion, I was like, yeah, here I could use it. Here recursion would be a problem. I wouldn't say it fails because I know it's technically possible to optimize it for recursion, but what you can do is you can go here and just add those guys to some kind of queue or to some kind of stack as in recursion, because you really doesn't matter what is order of going with this. You don't look for closest path or anything. Ordering of visiting those guys doesn't matter. If it is in your waiting set, you just need to visit it, and actually vector is probably the easiest way to do it. So you go here and you push those guys to the vector, to the stack using a vector. Then you take this from the stack, add this and this. And the only thing is to, okay, so what do I do with this fulfill? The thing here is that first of all, so you want your fulfill to stop at some point, because if you do just that, you go here, then you go here, like here, and this becomes a problem, because then you try to add this back to a queue and you go into, you know, infinite loop between those two. It is not the best idea. You just need another set, whatever you want, some container which would mark where you would mark already visited positions. I just use hashset for this. In this very case, it's good enough. So you need to make sure you never visit your square twice, and then additional thing you need to do, you need to count how many edges you encountered for this very particular case, because normally fulfill just, you know, visits every point at once, right? If you fulfill this, you can notice that you never add anything from inside, right? So you will just visit every single square at least once, and you need to make sure you visit them all exactly once. Sometimes in fruit fill you can, you know, visit something twice, which is not good because you hit your performance, but it would still work. Here you need to make sure you are visiting things once, because when you visit a thing like here, you need to count how many edges you encountered, right? So you go here and then you mark this edge. You go here, then you mark this edge, right? This is what you do. And in fact, you basically compare if the neighbor you want to add, if it is the same color, or if you should even visit that. So this is basically the easiest solution I figured out. By the way, my first attempt was maybe I should just fill those guys, right? And yeah, maybe, but it is not clear how to proceed from that. And there is one problem of the solution you need to keep in mind: how to figure out your starting position. Because, for example, view 3, we want to count those two edges, right? And with this thing, we would not count this. This is wrong. And also, yeah, we could start here, but then we are stuck. So to solve this particular problem, the easiest way is to add a border around, because first of all, we know that we want to start from the border. Border is proper place to start from. And also it would add us this always this escape path from some places on the border. So this is additional little trick for this puzzle to keep in mind. Probably you can do this different way. I chose this way. So how I did that? First of all, I calculated those min y and z, and at this point I just by debug printing those, I realized that my space is 21 by 21, I think, or something like this, or 25, doesn't matter, it's like 20-ish size. And then I figured out that basically instead of using hash set, I just could use three-dimensional array or something like this, and I would fit in with memory. But it doesn't, for this solution, it doesn't matter. If you would go for leaderboard, for example, it doesn't matter, because you just need solution and it's faster to write anything. then thinking what's the best approach. You will never see the difference if you are going for leaderboard. If you are going for the fastest solution, then you can experiment which gives you better performance. This day I was actually going for quick solution, not for the good one. And yeah, so I have minimum and maximum because I need to calculate my border. I immediately calculate border by decrementing minimum by 1, I'm incrementing maximum by 1. Then what I do, I create my visited set, and what I do, I initialize it with my data. So I mark all points which are my cubes, which are my kind of my borders. I mark them as visited, so I will not visit them the easiest way. I don't need another comparison or anything. Then I have my Q, which is technically a vector. Simple enough, and I have my count. I could probably do some mapping or something, or to just return counts, or I don't know, to just iterate over everything. I don't know. This was the easiest thing. I could probably fold it the easiest way. I cannot just iterate over Q because I would need to update it. So it's like, I don't know, maybe some from function, iter from function. But doesn't matter. You can do this kind of mutations. It's not like you never can do mutations. I think that in Rust you should try to avoid mutating for as long as you can. When you are learning, sometimes you should avoid mutations even if it's painful, just to learn how to avoid them, to learn how to write faults, how to do that. But sometimes this kind of simple mutations, like how do I avoid those three mutations? I just create the from fn function and I just move them there, or I just do a fault and I make state, which is not good, bad. It is often very good, and it makes the mutation very limited. You exactly, you tell that in this very loop I mutate some things, only those particular things, but sometimes it's good enough to just do this, especially that my function is just this loop. So it would be just that fault and there's nothing else to mutate, there's no other state. Sometimes better way, think that resigning from mutation is extracting your thing to another function, so abstracting your algorithm, something like this. But putting this digression aside, what do? I do exactly the same thing. First of all, I go through my queue and I check if I visited it already. So I can add something to the queue twice, but I would just iterate it. I would just consider it once. I could also just check function before I add them to queue, but I found this thing easier also because inserting just gives you back your information if there was something there. So I can just try to insert it into visited, and if it returns me true, then I just continue to skip the loop iteration. Someone could argue that continue is a bad habit, so he can just remove this bank and then wrap all of this in this brackets. And I would say that continue is not the best thing to use, and it makes it a bit more difficult to read the algorithm, but infinitely indenting is even worse. So I chose this thing. Then I get my nate balls and I don't use array. I just collect them to vector because I immediately want to filter those which are outside of min max. So I don't need to bother about them later. I don't go like infinite. It's just simple enough. I ignore anything outside of my bounds. Then I increment my count by what? But how many nate balls, either copy for convenience, are in my data. So I just figure out how many edges I just occurred, and then I count those edges and I do count. And then on vector I can just use extend to immediately push iterator into the vector. So I just extended it, and part 2 is done. It is so fast that you don't care about making faster. Probably you could use this base to learn some micro optimizations you can do on your code, but I don't think it's worth it in this case. This is example of very simple script, very simple solution. Okay, so thank you for watching, and this was today's very easy advent of code. Today was easy, so tomorrow I prepare for the worst, especially that this is the last week, I think. So yeah. See ya. Bye.